So this is how it's normally shown in theory. You have a controller. The output goes to a summer block with an external disturbance, unmeasured or measured, and that becomes input to a process. The output is then measured, fed back to the set point, subtracted from the set point to give an error, which goes back into the controller. And this is how it's shown in most textbooks and how it is taught in university, and you can see it's in the Laplace domain. This Laplace domain transform, however, needs to be put into a discrete or Z domain, and this is normally done in this fashion. So error is PV minus set point, or can be changed, depends on what DCS system how it defines it. They then calculate the delta error at times t, or time t, which is the error at time t minus the error at t minus 1. In other words, to calculate delta error at time t, you need two error measurements. Then the output is basically, well, the delta output is proportional to some constant kp, and there's the values inside the bracket. Now you'll notice it's actually a function. Delta output is proportional to delta error, actual error, and then the double difference of the error. It's quite important, and this is known as the PID algorithm in its raw format in the Z domain. Now there are variations of it depending on whether the PID algorithm is going to be used. You get another form which is I-PD, and this is where the PV is used instead of the error. So you have a delta PV at times t at time t, which is the PV at time t minus the PV at the previous time interval, and you'll see that the error term in the previous equation, or the delta error term in the previous equation, is replaced with the delta PV. So this equation at the bottom here is known as the I-PD because the error is used in the integral, and the delta PV is used in the proportional and derivative. So the first one at the top right is the PID because error is used in all three terms. The bottom one is I-PD. In other words, error is in the integral term, and the delta PV is used in the proportional and derivative terms. And this is quite a common variation of how it's implemented in many systems or DCS systems. You get different variations. I-PD, PI-D. This is an example of a Yokogawa extract, and it's manual. It talks through how it does them. You also have them in the Emerson system. In the DeltaV, you have various options. What is not explained in anywhere in the help files generally is that in reality you cannot take the actual raw delta PV or the raw delta error in a derivative term because of the instability that it can cause, clearly from noise or from measurement, either from error or from normal measurement. What is normally done, it's explained in a very good book, which is a worthwhile investment for any process control engineer. This book is PID Controllers. I think there's a later edition. I'm not going to try and pronounce the surnames, but in essence, what is done in most systems is the PV, or the term used in the derivative part of the PID algorithm, is passed through a filter. So I think this is basically a filter that kills all your high frequency noise. Now if you implement a PID algorithm without doing this, it can be shown that it be very, very unstable for fairly small settings of derivative values. So again, like I said, this book is a worthwhile investment. It explains very clearly why the derivative term is filtered and how it is filtered. Most DCS vendors or control vendors do not explain this in their help files or mention it in their help files, and they often don't even tell you what the filter values of N are that are being used.
So the first thing I'd like to try and get across is the concept of internal scaling, which is done by most control systems. So for most people believe that when they type in a gain into the controller, that is the gain used explicitly as shown in this equation here. This is not the case, however, because there's this value for kp, which is actually a function of some internal scaling factor times the actual parameter which is entered. So kc is normally the gain which is entered into the controller, and there's a ki value which is calculated internally by the DCS or by the control system. So if we want to just look at a proportional only controller, sorry, we're going to scratch out this. So we're just looking at change in delta OP is proportional to kp times delta error. So let's assume we have a flow transmitter which is ranged from 0 to 500 cubes an hour, and the output is in percent because it's going to a valve. The internal scaling factor is 100 over 500 equals 0.25. So for a gain of 1, the actual gain used by the controller, kp, is 0.25 for gain of 1. Now let's assume we have a sudden change in the flow, and let's take it. Now the rationale behind this is to have the scaling of the inputs and the outputs to be the same. In other words, if I go from 0 to 500 cubes as an error, I should go from 0 to 100 on the output for a gain of 1. That's why the internal scaling is done. So let's assume we have an error at time t, at some time, let's say delta error equals 50 cubes an hour. So now the delta OP equals 0.25, because that's what kc times ki will give you, times 50, which gives you 10%. So 10% change in the output, or the error, gives you a 10% change in the output. And that's for the reason why they do this internal scaling. Now let's just say you assume you have tuned a flow loop or a loop with proportional action only, and let's assume it's working fine. And for that you had a controller gain of 1. Now for some reason the process engineer decides to rescale the transmitter. So they want now the transmitter to be rescaled not from 0, so the flow originally was 0 to 500. Now they want to change it to 0 to 1000. Now the minute that has been implemented on the system, the internal scaling factor is now going to change. It's going to be again 100 divided by 1000 this time, which gives me 0.1. So we've just gone from 0.25 to 0.1. So the original kp was 0.25 for a gain of 1, for kc of 1. Now the new kp is going to be 0.1. So just by rescaling the transmitter, or if you have the flow transmitter, you have now actually changed the feedback loop used controller gain. So it's very important to make sure that in the event a transmitter is rearranged, that consideration is taken for the fact that the internal scaling is being used, and you would have to actually go back and correct the gain
So what I'm going to demonstrate here is just in a particular environment, which is the DeltaV or the Emerson system, how you would build a PID loop. So typically you have, this is your analog input channel, which you would configure to read in from an analog input, which I've shown in the previous videos. This is a PID loop here, or the PID block, and this would be an analog output channel, which would be used to you would configure the output of this to analog out, which would go into the field. Now what I've done is I've approximated the field value with this block here, which is a complex block, which has on this side over here, you can see I've placed the transmitter. This is the transmitter value. So what we have, it looks very much like Simulink. You have your analog input channel, which reads in the value from the field. Normally there would be an input here, 4 to 20 milliamp signal. It gets scaled to the PV value of the PID block. The PID block then does its control, and its output goes to an analog output channel, which is configured to the DCS or control system, and its output would then be converted to 4 to 20 milliamps and go back to the field. So all I've done is I've created a field here. This is this PV block. Things that are relevant to show here is the PV value that's coming in, the mode that the loop is in, shows cascade, which means says the required mode is cascade and the actual mode is cascade. In this particular DCS, you have an option to configure an analog output channel. So I can take that channel and I can put it into a different mode. So here we have the mode, and I can sort of, please put the, I'm working on that valve. Let's put it into manual. I'm going to physically take control of that valve. Now what you'll notice is that it goes manual, and it goes cascade initializing manual. In other words, it tells the master loop that this loop is that the output channel is no longer participating, and I can go and adjust the output value and say I want the output to be 20% or 15% only. What you'll see is that this information gets fed back to the master loop to tell the master loop's output to track it. So this is how the initializing gets done. You can see the flow measurements now. Is the raw field value, well, the actual theoretical field value, and this is a value that's a function of the turn down and noise on the transmitter. So we can put this loop back into cascade, because that's how it would normally run unless you're doing maintenance on this valve or the output channel. What you can also see in here is here we have the cascade in placeholder, so that we want this loop to run in cascade with a set point of 800 at the moment. We can pull up its faceplate, and that would be this faceplate here, which shows you it running in cascade. So we can put the loop into auto, and you can see it goes to auto, and let's put the set point to a reasonable range, which is sort of in the middle. It's 2000. You can see the PID loop responds fairly quickly. Unfortunately, it's shown quite badly here, but there's the history. Set point PV output. So what I want to demonstrate now is just how the proportional action works for a PI-D and an I-PD. So we have this particular controller I've now detuned. So it's got almost no, the integral effect is negligible. The controller type is PI-D. Now we have various options. and we can make it just a PD, but I'm just going to leave it PID for now, but I made the reset time very, very long, so it's going to have a negligible effect. I want to show you what happens with the PID versus an I-PD. So here's the trend. We have the trend here. Unfortunately, the lines are not so great, but set point is in white. Let's make the set point something slightly different. Okay, so set point is in red, the PV is in green, and the output we can make that in a dark blue. That's all scaled on the same scale. We can move this down slightly, so the output's not overlapping. So what I want to go to is to this block here, and we're going to basically make a fairly big set point change. At the moment it's in auto, so I'm going to put it into cascade. We can do that. I'll put it into cascade. Set point is still 2000. Now we're going to bump this up to 4000. Remember, there's almost no reset. It's proportional action. Now you'll notice that when we did that change, the output initially kicked, and because the PV did follow, eventually that's a proportional action effect. So you can see there's no integral reset effect, but this is for a PI-D. Now if the integral effect was in place, you would see it would integrate back up, but this is just because at that time interval there we had this sudden kick in the flow. So at this time interval here, at that time interval there, we had a kick in the set point. That effect that you see there, that initial rise there, is the proportional action. Then this decay here is also a proportional action because of change in velocity of the PV, which is shown there. So this is what you would typically see for proportional or PI-D where there's no integral effect. I'm going to change it, let the system stabilize, and I'll give you a demonstration of what it looks like with an I-PD. So here's the same problem. I have now changed this particular controller's mode to be an I-PD only, and it can be shown there. It's interval action on error and PD on PV. So now I'm going to show what happens when I do a set point change. Now again, the reset time is very large, so I've basically made the reset time dead in the water. Now we're going to change that set point to 4000. And if we go back to the process history view, you can see the set point change. And I made the PV orange in this particular case, but you can see the PV is not doing much because the OP is doing almost nothing. Previously here I reset the set point back to 2000 with the PI-D, and you can see it nicely resets. Here nothing happened. Let's go back and change reset time to make it a little bit more responsive. Let's make it 20 seconds. And now you can start seeing the output starts to move. And what I'm trying to show you or demonstrate to you here is that with this particular set point change, because I'm not using the error in the proportional term, there's no kick in the output over here. So one would normally expect to see at this point here, when we do the set point change, for a set point change we would expect to see this kick and then it's come down like we would before. It was proportional action, but here we don't see that because the error term is not being used, the PV term is being used, and the PV for this particular area here is constant. So you can see it's a constant, and the system slowly goes back to where the set point is. You can see it's not catching up. Eventually it just takes a while. So that's an I-PD algorithm. Now I'd like to demonstrate what will happen if you have normal settings for a flow loop of this type. In this particular case, what I've done is I've exposed some of the settings here, so you can see that the gain and the reset are reasonable for this particular problem. So let's once again do a set point change to 4000 and have a look at that, how it looks, how it differs to the previous examples that we saw. Now previously, when there was no reset time, if you recall, and I'll show you alongside, the proportional action and effect where it came up initially like that, and then it came back down because there was no integral time or reset time. Slightly different now, you have the initial kick and then the reset time kicks in to bring you to set point. And that gives you the full effect of the PID algorithm. Now I want to demonstrate for you what happens when we put it back to a PID algorithm, again with a fairly large reset, but this time I'm sticking the valve. In other words, although this is sending a set point or an output of 40.005, internally the valve has actually got stuck. Now I'm going to do a set point change, proportional action only, because we've basically made the reset too large. Let's see what happens. So I'm going to bump the set point back to 4000. You'll notice output jumped to 60%, but internally the valve is actually stuck. Now look very carefully. For proportional action only, we see what we had before. There's the initial kick in the output. So what we see there is the initial kick. That's the initial kick in the output. But now because the valve is stuck, the PV stays constant. PV is constant. And because the PV is not changing, its velocity is 0. And the error at this point here, the velocity is also 0. The change in the output is 0. So your output doesn't move at all. So that gives you an indication of how this differs to when the valve is not stuck. So now I want to demonstrate what will happen if we had a valve that got stuck while we were doing set point changes. So once again, reset time is in essence, it's a proportional only controller, and I've added this extra feature drift, so I can drift the valve and I can stick it. So it's not stuck at the moment, and the drift is going to go from, it's basically a bias, it's going to go bias the output from 0 to 100 or full scale. So let's first stick the valve, make the valve stuck valve, and once again we're going to take the set point to 4000. And as we can see, once again, proportional action kicks in. Because the PV hasn't changed, there's no change in the PV, only the error changed for that one scan cycle. You have a kick in the output. It's your proportional action on error only. PV is not changing now. Integrals basically has no effect, so you've got no effect on the output. If you go back and look at you'll see the output is slowly changing, but it has no idea that it's stuck. Now we are going to enable the ramp, and the ramp time is over 60 seconds, so we can make it slightly longer than that. Let's make it 90 seconds, and we're going to start to enable the ramp. So now you'll start seeing it will start ramping up and biasing the output. Now what actually happens is, now the PV in the field is actually going to start ramping up. With proportional action only, as you can see here, the velocity or the change in the error is a constant. So the slope of this curve is a function of the slope of that curve, because the delta error in this region over here is the velocity is basically constant. So the velocity of the output will be constant. Now the golden question is, there's the set point there. Output is doing this. What happens when the PV crosses the set point? So in this region over here, the delta MV, excuse me for a second, is proportional to basically a constant, or proportional to the delta error. And the delta error here is changing, so it's constant as the velocity. Now when it crosses this transition point here, the question is, does this continue to move down or does it change direction? Now as a general, because of the way things are taught at university, there is a feeling that it will change direction often. But as we can see, that's not what happens. Even when it crosses, even at this time point here, when the error changes sign, in other words, we do not get a change in the output of the feedback loop. And that's quite important to understand. So this is what would happen with proportional only controller. When the PV is going up, your error is going to go down, and there's going to be no change in direction at when the error goes to 0. So it's quite an important concept to understand. Now I want to introduce the concept of turn down on a transmitter. So as I have here, there's a turn down ratio. So in other words, the transmitter can read very accurately at 100 to 1 turn down. And typically, as you turn down, as the flow gets lower and lower and lower, it tends to get biased because of the area of inaccuracy at turn down. So there's a bias, which is a fraction of the range of the transmitter, and there's noise, which gets added to the signal, which is a fraction of the range of the transmitter. So these are three parameters that I've used to model turn down and the effect it has on flow control. So if we now change the turn down ratio to a number that's potentially close to what an orifice is like, 3 to 1, and we leave the bias at 0.1 and the noise at 0.1, it's 10% of 5,000 is a fair amount. We can start to see already that there's some noise in the transmitter. Not much, there's a bit of drift, but it really is not a lot. Now when we're starting up a plant, we don't normally start up at the design case, which would be in a reasonable operating region. It's normally closer to 0. So now I want to demonstrate what happens as we bring the set point down. So we're going to go down to 2000, which is still not a problem because it's 2/5. It's not going to be an issue at this point in time. PID, then we just get the resets back to where we want a reasonable reset value. Make a fairly quick controller because I think it's designed to be fairly small. Overshot a little bit there. And everything's great, so that's caught the controller. So it's in control. Now we're going to bring it down even further. 1,000. Take it to 1,000. Start to see the effects of the turn down problem. Should start to see a slightly noisier signal. You can start seeing the noises coming through. And there's some drift. 1 second interval is probably not ideal now either. There's a bit more noise. We turn it down even more. 500, which is fairly close to down. We've got more noise in the signal. This is actually still very good. Normally it's a lot worse than this. Probably increase the noise somewhat a little bit more. Here you can start to see the noise. And now we want to control that at 200. This is actually still doing fairly well because it's a 10 to 1 now and it's still reading right. So the bias, I would probably take that bias up a little bit. And you can start seeing the effect of the noise. But you can see the actual flow is at 1,500, but because of the error in the measurement, we're only seeing 493. And when we get to close to 0, you can start to see that the flow reading at this point is very, very noisy. And it's bouncing around close to the 0 point. This is what normally happens in the real world with flow transmitters. So although we're showing a zero value, the actual field value is about 1,000. So what happens now is the controller starts going through an oscillation as 0. It starts opening the valve until there's a flow measurement. And the flow measurement becomes valid. And you start getting a seesaw effect on the output of the controller. So run for a short while and I can demonstrate it again a little bit better. What you can see over here is the PV goes to 0 here. The output goes up, and then eventually at some point you've got enough flow through the orifice transmitter that you do get a flow reading, so it starts coming up. The flow reading recovers, and because it suddenly recovers, it overshoots. The output goes down again, and once again it goes to 0. Then it goes up, and you start getting the seesaw effect, which is quite common in a turn down case. And that's how it looks as it continues. So this is a fairly good, it's actually fairly well behaved. It's normally a lot worse than this.